just going to talk about derived rules. So the primitive rules allow us to prove every valid sequence in sentential logic. So we can prove everything using just the primitive rules. But we often encounter the same situation again and again. And having done the proof once using the primitive rules, we can always just refer back to that proof. And I just want to work through a single example here. So here's a sequence which is intuitively valid, right? Either P or Q, if P then R, if Q then R, therefore R. This tells you either P is true or Q is true, or maybe they're both true. If P is true, R is true, and if Q is true, R is true. So R's got to be true. So with the primitive rules, we're going to have to use reductio. Here are our three premises, a disjunction and two conditionals. And the elimination rule for the disjunction and the elimination rule for the conditional are two-line rules. Wedge elimination requires you to have the denial of one disjunct in order to get the other. We don't have the denial of either of those disjuncts. And arrow elimination requires you to have the antecedent of the conditionals, and we don't have P and we don't have Q. So proving R from 1, 2, and 3 can't be done by an elimination rule, and it can't be done by an introduction rule, because this is an atomic sentence. So we'll have to use reductio, which means on line 4, we assume the denial of what we want to prove. Well, what we want to prove is R, and so we assume not R. For reductio, well, now we have to prove two sentences that deny each other, any two sentences. So it could be P and not P, could be Q and not Q, could be R and not R. The reason to choose R and not R is because we already have not R. But on the other hand, we don't have an easy way of producing R. The trick here is to assume one of the disjuncts of 1 for reductio, prove its denial using reductio, that will give us, say, not P, then we can get Q by wedge elimination, and then we can do another reductio. So let me show you how it works. Here we assume P also for reductio. We could assume Q instead. It's arbitrary, which we do. 2 and 5. Here now, here's the conditional, here's its antecedent. So 2, 5, arrow elimination gives us the consequent of 2, which is R. So we've used assumptions 2 and 5. But 4 and 6 can't both be true. 4, 6, reductio, discharging 5 by denying it. So we get not P. 4 rests on 4, 6 rests on 2 and 5. We're discharging 5, so the assumption set here is 2 and 4. Not P is the denial of the left disjunct of 1. So 1, 7, wedge elimination, we get the other disjunct, Q. So now we've used 1, 2, and 4. Q is the antecedent of the conditional on 3. So 3, 8, arrow elimination, gives us the consequent of the conditional on 3, which is R. Now we've used 1, 2, 3, and 4. And now we're done, because the sentence on 4 and the sentence on 9 cannot both be true. So 4 rests on itself, 9 rests on 1, 2, 3, and 4, and so if we can't maintain all of these assumptions, and so we deny the assumption on 4, and we get R by reduction. So what this means is that whenever we have a disjunction and we have two conditionals that have the disjuncts of that disjunction as their antecedents and have the same consequent, well, we can just go straight to the consequent, and we cite the rule, which in this case is called simple dilemma, or simple dilemma. Whenever you have a disjunction and two conditionals with the disjuncts of that disjunction as the antecedents that have the same consequent, then instead of going through this whole proof, you just refer back to it. You just say, hey, I've got a disjunction, two conditionals with the disjuncts as antecedents that have the same consequent, so the consequent must be true. And that, after all, is what this line says. And in principle, any line in a proof, because it represents a valid sequent, could be turned into a derived rule. But it's only useful to do it for the situations that we encounter often. Simple dilemma might be one example of that. Complex dilemma might be another. De Morgan's laws, modus tollendo tollens. We have a whole bunch of derived rules. You're allowed to use the derived rules once you've done the proof using the primitive rules. But you can't prove anything with the derived rules that can't be proved with the primitive rules. So the derived rules are a kind of shortcut referring back to a proof you've already done. If you haven't already done the proof using the primitive rules, you're really not entitled to use the derived rules. But once you've done those proofs, then the derived rules take the place of significant chunks of proof, right? In effect, we would take the place of two reductios here, as well as these arrow elimination, wedge elimination. So the derived rules do not strengthen the system, and they make the system more complicated, which is in many ways a bad thing. But on the other hand, they shorten the proofs, because we basically refer back to an earlier proof, say, you could drop that earlier proof in here, but I don't need to do it again. Don't make me do it again. I've already done it once. So they shorten proofs, but they make the system more complex, and they do not strengthen the system. There's nothing you can prove using derived rules that you can't prove using the primitive rules.